How to deploy deep learning models on resource-constrained robots. Imagine trying to teach a tiny robot to recognize objects or navigate a room with only a small brain and limited energy. That's the challenge many robotics engineers face today. When working with robots that have low-power processors, small memory, and limited sensors, deploying deep learning models becomes a puzzle. These robots often run on microcontrollers or edge artificial intelligence chips, which are much less powerful than computers. They also have limited battery life, so heavy calculations can drain their energy quickly. Plus, their sensors might only give partial or noisy data, making perception harder. To make deep learning work on these tiny robots, engineers use several smart tricks. First, they focus on model compression. This means shrinking the size of the neural networks by removing unnecessary parts, called pruning. They also reduce the precision of the model's weights from 32-bit floating point numbers to 8-bit integers or even fewer. This process, called quantization, helps models run faster and use less energy. Another technique is knowledge distillation, where a smaller model learns to mimic a larger, more complex one. This way, the robot gets a leaner model that still performs well. Choosing the right model architecture is also key. Instead of using big, heavy networks, engineers pick lightweight models like MobileNet, SqueezeNet, or EdgeLite. These are designed specifically for devices with limited resources. They strike a good balance between accuracy and efficiency, perfect for tasks like recognizing objects or detecting hazards. Running these models efficiently requires special software tools. Frameworks like TensorFlow Lite, ONNX Runtime, or custom robot operating system frameworks are built for low-resource devices. For example, TensorFlow Lite allows models to run smoothly on microcontrollers and small chips, making real-time decisions possible. Some frameworks even integrate directly with robot control systems, like the robot operating system, to streamline deployment. Since sensors on small robots are limited, combining data from different sources can improve perception. For example, fusing camera images with LiDAR or sonar data gives a clearer picture of the environment. Also, processing only relevant parts of the sensor data reduces computational load and saves energy. Some robots can even adapt their models on the fly. Limited on-device training or fine-tuning allows the robot to improve its performance over time without needing to connect to the cloud. This keeps data private and reduces reliance on internet connections. Managing energy is also important. Robots can schedule their deep learning tasks during times when the battery is full or switch to low-power modes when idle. They might only run intensive perception tasks when necessary, like when approaching an obstacle. In practical terms, these strategies help robots navigate indoors, detect hazards in retail stores, or recognize objects for manipulation tasks. For example, a small robot in a supermarket can use a lightweight neural network to spot spills or obstacles, helping it move safely without draining its battery. All in all, deploying deep learning on resource-limited robots involves making models smaller, choosing efficient architectures, using specialized software, and managing energy carefully. These steps let robots perform smart tasks without needing powerful hardware, opening new doors for robotics in many fields.